In today's lesson, we're going to be describing solid friction that is both static or dynamic by their coefficients of friction. We will be doing this on flat surfaces as well as inclined planes. Friction is a force, and it is a force that bodies impart on each other when they are in direct contact. So this is a contact force. It is either when a body slides over the other or if the bodies cling together despite any external forces. They are parallel to the contact surface that they're touching. It creates heat as a waste product, and it does have an action-reaction pair. Every surface has irregularities. They are jagged, peaks and troughs and dips, and these, when two objects collide and they scrape over each other, they give rise to a force that resists the motion. Depending on how many troughs and peaks there are, will dictate whether or not they have a high level of friction. And what causes this is electrostatic attraction between the atoms of the contact, which make it crash into each other and not allowing another object to slide over it. There are two kinds of friction, static and dynamic. Static friction is when there is no relative motion between the bodies. If you are pushing a block, it does not move. This is static friction. So over here you see a free body diagram, a box here, which is being applied with some force. It also has static friction denoted as a little f sub s. Here is the weight of an object that is acted upon by gravity, and above, in its opposite direction, is the letter R or N, and this is known as the normal force or the force of reaction. So it's the normal reaction force. It can be denoted as an R or an N, and you will see them used interchangeably. I will do my best to use R. And in this case specifically, you can see that the net force is 0. The object is staying still. It is at rest. Imagine pushing a block. This is just an example. If you're pushing a block, it doesn't move, then you know that the friction must be equal but opposite to the pushing force. So here is where you have static equilibrium. You have the friction matching the application, the applied force. As you push harder, the object is still not moving. The friction force grows with the pushing force. So as you continue to push, the friction will match the push until the block just starts to move. There is a formula for static friction, and this is denoted as friction force is less than or equal to mu, and this is the coefficient of static friction. There are no units, and it is multiplied by R, which is the normal reaction force, also known as F sub n for normal force. The reason why the coefficient of static friction has no units is because if you look over in the equation, here you have friction force, which is denoted in units of newtons, and the reaction or normal force also is in newtons. So if you were to solve for mu, it is in relation of newtons per newtons. So the newtons would cancel out and you would just have a value. In regards to static friction, so the symbol that is less than or equal to means that the friction force can be 0 to a maximum value. If the value is less than the max pull force, the block will stay still. The friction force is at the max pull force, then the block is almost about to move. So it is reaching that point. And then if the friction force is more than the max value, the block will move and become dynamic. With dynamic friction, once the block begins to move, the friction force drops. If the same force is applied that was used to start the block moving, then the block would actually begin to accelerate. Here is a graph that shows the amount of force applied in relation to the amount of friction that is experienced. So here it starts with 0. As you increase the amount of applied force in newtons, the amount of friction also increases until it reaches a point where the object begins to move. And then you'll notice it is called also kinetic friction. Dynamic friction is the same. What you'll notice is at this threshold of motion, then mu will not be static anymore. It will change to a value which is mu sub k or mu sub d for dynamic. And notice here that it drops, and then you're able to accelerate or just keep a constant velocity for your object that you're moving. But it does take a certain amount of force in order to push it past the threshold at which the object will begin to move. So dynamic friction is when two surfaces move past each other. When you are pushing on an object and it is moving, the object is under dynamic friction. It is experiencing dynamic friction. It has dynamic friction. Dynamic friction is weaker than static friction, as was seen in the last graph. And down here, you'll see a free body diagram where the friction force for the dynamic friction goes in one direction, and the applied force is greater than that of the friction, which is where the net force is moving the object to the right, and acceleration is also experienced. The formula for the friction force for dynamic friction is denoted as friction force equals mu sub d times r. And remember that r is the normal reaction force, also known as normal force, and is also denoted as the capital N or F sub n. The coefficient of the dynamic friction here is also unitless. And just remember that the coefficient of friction does depend only on the nature of the two surfaces that are in contact and how they interact, not so much the surface area. Friction on a flat surface. Here is an example where a dog of mass 4 kilograms is sitting on a horizontal cliff top. The dog is experiencing or has a coefficient of static friction of 0.7 and a coefficient of dynamic friction of 0.3. A horizontal force is provided and gradually increases until the dog starts to move. Find the acceleration of the dog as it starts to move. Here are the arrows for the dog's weight being pulled down by gravity and the normal force that is pushing up against the dog. The first thing that you want to do is to find the dog's weight, which is weight equals mass times gravity. And we have 9 kilograms times 9.8 meters per second squared, which gives us 88.29 newtons. At the point where the dog just starts moving, we can use this equation. So we have F equals mu sub S times R. We have been given the coefficient of static friction as being 0.7. We multiply that by the R, which is 88.29 newtons, and we get a total of 61.8 newtons. As it starts moving, the friction force does drop and becomes dynamic friction. So when the friction that we're trying to find now when the dog is moving is mu sub d times n or r. And so what we have is 0.3 times 88.29 newtons, giving us a total of 26.487 newtons, or rounded off to 26 newtons. The net force when the object starts moving is going to be the two forces subtracted from each other. So we have 61.8 newtons minus 26 newtons gives us a net force of 35.8 newtons pushing to the right. Acceleration is experienced by, remember that force equals mass times acceleration, so if we were to solve for acceleration, we have the net force over the mass, which is 35.8 newtons. This is the net force divided by the dog's mass, which is 9 kilograms, giving us 3.977 meters per second squared, which is rounded to 4 meters per second squared. So we are going to be experiencing the dog being pushed off and eaten. Here is an example of friction on a flat surface. We are given a 15-kilogram piece of wood and we place that on top of another piece of wood. There is 35 newtons of static friction measured between these two items. There is no applied force. You just happen to know this information. Determine the coefficient of static friction between the two pieces of wood. So we are given the following information, and I'm just putting in the vectors for the top piece of wood that is placed atop the second piece of wood. And the red line over here is the friction force, which was already given, and it would go in this direction if we were moving the object. I just wanted to show you where it would go. So step 1 is to find the wood's weight. When you do that, it is weight equals mass times gravity, and your answer should be 147.15 newtons. Step 2 is to go ahead and find the coefficient of static friction, and this is the equation here with R being the normal force. When you plug everything in, you should get an answer of 0.24 with no units of measurement. There will be times, however, where possibly you might be asked to find the coefficient of dynamic friction, or even possibly the static friction, where an object is being pushed at a specific angle to the horizontal. For example, a 5-kilogram box is pushed across a level at a constant speed with a force of 100 newtons at 28 degrees to the floor. Calculate the coefficient of dynamic friction between the floor and the box. Here is my diagram with all of my information, and let's go ahead and solve. So here's what I have. Everything is here, and I've also already solved for the weight. So the weight is 49.05 newtons. One thing to note is that because this problem specifically stated that the speed is constant, we know that the net force is going to be 0, and that is going to be in my x components as well as my y components. So the sum of all of my vectors for x will equal 0, and all of the sum of my vectors for my y will also equal 0. So we're going to break them up into their components. And here is my x component and my y component given the angle of the force. And then I also do have a few other y particles, and here's another x component. So let's go ahead and find our x components. What I have here to solve for x is 100 newtons cosine of 28 degrees minus, this is going in the opposite direction of my applied force, so therefore friction is going to be negative. We set that to 0, solve for everything that we can here with the calculator, and we get that the force of friction is going to be 88.2947 newtons. Over here for the y components, we are going to look over here and we're going to see if whether or not we have to add or subtract our vectors. We have the y component here going down, which is 100 newtons sine of 28 degrees, plus the same direction is the weight, so we're going to add that, 49.05 newtons. And then we also have the normal force, which is going in the opposite direction from the initial y component direction. So that is going to be negative. When we solve for everything, we get R equals 95.9971 N. Now that we have that information, remember the equation that goes for solving for friction. So we have the friction force equals mu sub d, which is the coefficient of dynamic friction, and that is multiplied by R, which is the normal force. Plug everything in that we have, and you should get an answer of 0.91, or after all of the sig figs are taken into account, I have 0.9. Here is an example. When you are trying to find the coefficients of friction on inclined planes, and this object here is stationary. And notice here that it does have an angle of 30 degrees. and given a mass of 10 kilograms. You are asked to find the coefficient of friction. So what we do know is that the mass, or the weight, of the object is down straight to the ground here. However, you're going to notice that the normal force is at a different angle. It is actually going to be placed at a perpendicular angle to that of the actual plane that the object is on. The first step that you want to do is to find the weight of the object. So given that we have 10 kilograms for the mass, we just need to multiply that by gravity to get 98.1 newtons. Here is the diagram again, and notice that we have two red lines here, and the reason why is that when you're trying to find the coefficient, you can't get it straight from this weight. And what we know is that gravity is pulling on the object, and there are two components. So you're actually going to need to resolve gravity by breaking it into two components. It does have a parallel right here where it says force and it's parallel. And then it also has a component that is perpendicular. And we are going to denote this by F sub perpendicular sign. What we do know is that because this angle right here is 30, we also know that this angle right in here is also 30. And this is based off of trigonometry and geometry if you know your rules. If you don't know the rules, you can refresh your memory by watching this video here, by going to Khan Academy and then looking up inclined planes and friction. I will also put it down in the bottom of the footnotes under the video. Step 2 is to resolve the force of gravity into two components. So we mentioned that there is parallel component, which is also known as the net force. And then there is the perpendicular component, which is equal to R. It is in its opposite direction of R, and these two are exactly the same value. So what you want to do is to just draw this line right here connecting this perpendicular component with that of the weight of the object. When you do that, you'll notice that you have a right triangle right here. And this is going to help you in order to find the net force, which is the parallel component. If you solve for this, this is also the same value. So we know that this angle right here is 30 degrees. So from here, we can say the sine of 30 degrees equals the F sub parallel over 98.1 newtons. For our perpendicular component, we have cosine 30 equals the F sub perpendicular over 98.1 newtons. This component and this, remember these two, are exactly the same. So if you solve for the perpendicular component, you will also get your normal force. So let's go ahead and solve for the parallel and perpendicular components, and we should get 49 newtons and 85 newtons. So here we have all of our information on our diagram. The next step is finally we can solve for mu, which is the coefficient of static friction. When we plug everything in to our equation to solve for the coefficient of static friction, we will get 0.58 after rounding everything off. Now that we've done it a longer way, I'd like to show you a shortcut, and you're going to love it. Okay, so as long as you know the angle of the ramp that the object is sliding on, it is going to be so simple. So we know that the components for the y is 98.1 newtons, cosine 30 degrees. Down here, the x component was 98.1 newtons sine 30 degrees. What if we just took the tangent of 30, which is opposite over adjacent, and what we get is that our newtons, our weights on both sides, our forces over here, they're going to cancel. So all I'm left with is sine 30 degrees over cosine 30 degrees, which is the same thing as tangent of 30 degrees. If you were to just take the angle and take the tangent, it would give you 0.577 or 0.58, which is the same answer as the last slide. All right, we've made it to the end. Hopefully everything makes sense, and we're going to practice this in class next. Have a wonderful day.